Thank you, Dave. And I want to thank all the organizers, Aaron, Emily, David, and Stuart, for giving me the opportunity of speaking here and also for organizing this great event. And also thank you to all the people in IPAM for putting this together. Since I'm the last one, I'm using this time to do that too, to thank everybody. So I will talk about the classification of small fusion categories. I have results on this topic, and a lot of other people has results. This is a big program of classifying these kind of categories. So let me get started. At this point, you might be convinced already that fusion categories are interesting, but let me tell you a little bit why I really love this topic. I enjoy a lot this topic because it has a lot of connections with many, many areas of math. As you might have seen already, there are links to VOAs, conformal field theories, TQFT. It's related with representation theory of various things, quantum groups, Hopf algebras. More on the analytical side, we have connections to subfactors and von Neumann algebras, links and nodes invariants in the topological side, and also physics. It's very useful, or it has connections to topological phases of matters and topological quantum computing, among other things. And I also like that they are natural hosts for quantum symmetries, and that's one of the reasons of the connections to physics. So as groups play an important role in classical symmetries, fusion categories are the unifying language for quantum symmetries. So for this, when there are some symmetries in quantum settings, we can see them using fusion categories or tensor categories, possibly more generally. So why we classify? For many reasons. One is because we want to advance and know more about these objects. And the things that are good about classifications are, for example, that we can find new examples. So while people was classifying fusion categories of certain dimension, they found families of categories. For example, the 2-Ising category. I might say something or not about, n-Ising category. That generalizes a nice category that it's called Ising, and it's a modular category, and it's very important. And they were classifying certain specific type of fusion categories, and they find that there is actually an infinite family of categories generalizing this one. Also, we are in the early stage of fusion categories in some sense. We don't know that much about fusion categories, and actually we don't have that many examples as we would like. And most of our exotic examples come from the classification of subfactors. So classifying, it's very useful for us to understand better these structures. Then also via classification, a lot of times we find inspiration to get new constructions, like we construct new categories from given ones and maybe using groups or other things. So there are two constructions that I have been working on, gauging and testing, and both of them were inspired by classification. And even when you want to understand the categories and you are thinking about them, some nice theorems or invariants or properties were also inspired by classifications. For example, the Cauchy theorem, that it's a generalization of the Cauchy theorem for groups in the context of modular categories, and was something that people believe because of some examples and so, but classification was kind of the thing that pushed to get the proof done. So that's kind of a motivation for my talk. I know that you have already heard from many people the definition. I will go over just very quickly because I want to mention invariants related to these categories, and I want to point the different things that I will use. So a fusion category over the complex numbers, or C is a fusion category over the complex numbers if it's an abelian C linear category. So I have direct sums, I have a zero object, I have home spaces that are vector spaces over the complex. My category needs to be monoidal, so it will have a tensor product, an associativity constraint satisfying certain diagrams, a unit object for this tensor product. So this is monoidal structure. It's also rigid, so we have duals for our objects. and are not just duals, they have an evaluation and a co-evaluation map that satisfies some nice zigzag equation. Then my category will be semi-simple. So every object will decompose as a direct sum of basic blocks that are my simple objects. My category has to satisfy some finiteness condition. This finiteness condition is asking that these home spaces that are vector spaces are finite dimensional and that I have only finitely many simple objects in my category up to isomorphisms. And I also want my unit to be one of these simple objects. So some other interesting class of fusion categories I will mention a little bit later, and so I want to introduce the name, are the braided fusion categories. So what I'm asking here is that my tensor product is commutative, and it's commutative in a coherent way. So it needs to be compatible or behave nicely with the associativity that this tensor product has. So I will have some nice braid between my objects here. And you will see that the braid usually it's represented like this, plus 2 hexagon axioms. And then C is a modular category. I will mention some results of classification of modular categories. If this braid is non-degenerate, and what means that the braid is non-degenerate, that if you do the square of the braid, so if you braid twice, so if you go once again and you braid, what you want to get or now you have a morphism that goes from X tensor Y to X tensor Y. We want this to be just the identity when for all the Y's in my category when X is equal to 1. So the only string that it's transparent for this, or the only simple that it's transparent for this braiding that I can interchange with any other object is my unit. And I also want to have some nice extra structure. Let's say that I have a nice trace, and I'm not being very specific here, but you have a nice trace. You can define some nice notion of dimension using it, and it behaves nice. So let me tell you some examples that I know that already some of them have been mentioned. So if I have a finite group and I consider the category of finite dimensional representations over my group, this is a fusion category. I'm over the complex numbers, so this category will be semi-simple. I will have only finitely many simple objects. I have the diagonal action to get my tensor product. I have the trivial action here. And using the inverse of the objects, I can create the duals. And to get these nice morphisms, I need here to consider finite dimensional representations. But this is not the only category that we can get with a finite group. And I think they've discussed this possibly in detail when he was in the discussion room on Tuesday. We have the category Beck-G omega, where, and this category is the category of finite dimensional G-graded vector spaces. So the objects are vector spaces graded by my group G. And here this omega is a 3 cocycle that Corey also explained in detail what this means. And what I'm doing with this 3 cocycle is I'm twisting my associativity. So I will have some non-trivial associativity for my categories. This morphism here that tells me how to put parentheses or how can I change parentheses when I do tensor products. Then other family of example or other source of example, maybe it's from subfactors that, again, this was already mentioned, but if we have a nice subfactor that has finite depth and finite index, then we can look at the category, and maybe here we need more space. So we can look at the category of NN by modules, and we will get a fusion category here. And then there are other ways to construct categories. One nice category is the so-called Fibonacci category. I will not describe all the things of this category. Maybe let me say something here. This finite depth will ensure that we have finite number of simple objects in the category, so that's important. Sorry. And then the category of Fibonacci is a category that has only two simples. And one is the unit and one is an extra simple. And when I do the fusion of this simple, this other simple, the x, with itself, I need to know what this is. This will decompose as a direct sum of simples, and actually it will decompose as 1 plus x. And it's called Fibonacci because if you want to look at what are the coefficients that will appear when you do the tensor product in this category, you will get Fibonacci numbers. So it's a nice category. And I will possibly mention more about this later. So one thing is that, as I mentioned, or the title of the talk is classifying small fusion categories, why we write small there. So as you see here, we already have that finite groups give examples. So to classify fusion categories, we need to keep in mind that we need to understand very well groups. And not only that, other example of fusion category come from Hopf algebra. For example, the category of finite dimensional representations of a semi-simple Hopf algebra. It's again a fusion category by very similar arguments than the ones here in the group case. And so if we want to classify fusion categories, in particular, we would need to classify finite dimensional semi-simple Hopf algebras. And that it's not done, for example, and it's not like we know exactly how to do that. So we see that in principle, classifying fusion categories in general is out of reach. As I mentioned, this is kind of an theory that it's in the early stages, so we are still trying to find more examples, understand more constructions and properties. So what we do instead is we try to classify using invariants, or maybe not only using the invariants, but putting some restrictions on certain invariants. So that it's what will give us the notion of small that I will mention later. So let me present some of the invariants that we look in the fusion categories. So the rank is just the number of isomorphism classes of simples. And as we mentioned before, this is finite number because my category is finite. And actually I will write here just for convenience here that the set of simple objects up to isomorphism will be denoted by IRC. I will have the 1 because the 1 is one of the simples, and I will have some number here. So R in this case would be the rank, and these are the simples up to isomorphisms, maybe the set of simples up to isomorphism. So what are the fusion rules of my category? This is a monoidal category. So if I take two of the simples, I tensor them together, I get a new object in my category. Now my category is semi-simple, so I can decompose this as a direct sum of the simples. And the fusion rules will be the coefficients that the simples, or with which the simple appear in this decomposition. So these are my fusion rules. Or in general, maybe these are the fusion rules. And associated to these numbers, these are how many times my simple xk appears in this tensor product. It's an integer number, so it must be 0. It's just the number of times, so it's a multiplicity. And using this, I could look at the matrix of multiplication by one of the simples. So the simple objects are the basis for my Grothendieck ring. So I could think of forgetting for 1 minute of the extra structure that I have in the category, all this natural isomorphism giving me the how my parentheses change and these kind of things. I could just think about the operation of tensor product and direct sum and the duality, the rigidity, and that will give me some nice ring structure. And it will be called a base ring, and it's a ring generated by these simple objects over set. And so I will look at the matrix of multiplication by this element xi, by this simple. If you look at the matrix, I will call it left multiplication, and I will just look at the matrix. So what I will do is, the bases are, again, these elements here. So the elements that I will have in the matrix are just the fusion coefficients, these coefficients that appear here, okay? And this is a nice matrix because it's a matrix with all non-negative integer coefficients. So by Frobenius-Perron theorem, this matrix has a maximal non-negative real eigenvalue. That eigenvalue, I will call it the Frobenius-Perron eigenvalue of the matrix. It's what it's called the Frobenius-Perron dimension of my object. And this will be always a real number. And in this case, it will be always positive. So this is a very important invariant that it's very useful when we want to classify. And using this, and maybe remember a little bit of what happened in group theory, the dimension of the category will be defined as the sum of the square of the dimension of the simple objects. Why I say to think about group theory, because let's think for 1 second of our example rep G, here the previous example. So the rank is just the number of irreducible representations up to isomorphisms. And here, when we compute the Frobenius-Perron dimension, what will happen is that it's just the dimension of the representation as vector space. And this dimension is the order of the group, because what I'm getting here is the square of the dimension of the irreducible representation. So I'm getting the order of the group. So in this case, for example, it's just the order of the group, and here some representation will be just the dimension as vector space. One comment that I want to make, in this case, the dimension here, or we have some examples coming from groups and from subfactors. Not all examples will come in that way. For example, we have some, or at least not all from the groups, and it's easy to see that when we have groups or some kind of representation theory, the dimension will be the dimension of the underlying vector space. But this example that we have for Fibonacci has a nice thing, and it's that the dimension of X, it's the golden radio. This dimension is a very nice function. It's additive with respect to the direct sum, it's multiplicative with respect to the tensor product, it preserves duality, and it's unital. So let me tell you a sample of classification results for small fusion categories. And what I mean with small, it will vary depending on who you ask. We can look at different invariants and try to classify depending on them. So there was a lot of effort of classifying by rank. Rank is the number of simples. Ostrich started this, and he classified fusion categories of rank 2, so only 2 simples, like the one of Fibonacci, the unit, and something else. And then when he went to rank 3, he already needed to add some restrictions. So we have classification, so rank 2, pivotal, rank 3, that this, it's maybe technical, it's again related with the nice trace in some sense. And there is a partial classification for rank 4. If we go to the modular case, so if we add the hypothesis that now we have much more structure because we have the braid, and moreover, the braid has a property that it's non-degenerate, then the classification was pushed further. It's known up to rank smaller or equal than 5. It doesn't look like very big, but it's the difficulty increases a lot when the rank increases. And there is some partial results of rank 6. A lot of people has worked on this, Paul Brulliard, Richard Eric Rowell, Stone, Wang, and a lot of other people. With some of my collaborators, we push this classification when we add the hypothesis that the dimension of your category is an integer number. So in this case, is rank known until rank 7. And then if it's odd dimensional, the category, with some collaborators, we push it up to rank, up to rank 15. And I will talk more about this case later. So other option is study the categories fixing the dimension. So you fix the dimension of your category and you want to see what you can say. I think of Jelaki, Nikshik, and Ostrik, and a lot of other people also work on these cases, and they classified or at least characterize sometimes what it could be when the dimension is a prime or a product of 2 primes or the product of 3 different primes. Or in this one, there are classifications result. In these other cases, P to the N or PA to Q to the B. There are more like characterization results. They can say nice properties. In this case, the category will be nilpotent. So there is a notion of nilpotency for categories, and in this one will be solvable. And if you see, there are similar results of things that you know from group theory. Now, if the category is modular, again, there was efforts to push the classification further in this case by a lot of people, again, Paul Brulliard, Don, Sonia Natalia, myself, Eric Rowell, and others. And we made efforts on classifying categories with dimension of the form P to the N times M, where P is some fixed prime and M is a square free integer, not divisible by P, right? It's like we take, and especially a lot of efforts were made when this P is 2, which is usually somehow more problematic sometimes, or gives some difference. A lot of efforts also were in classifying subfactors, a small index subfactors, and in this category you have the classification of fusion categories with one object that it's a tensor generator of your category, the object X, and then they bound the dimension of this object. And so a lot of people also work in this, Afzali, Scott Morrison, Dave Pennis, Kennedy, Michel, and they have results for this being smaller or equal than 5/1 over 4, 1/4. And and Kane has some results, for example, for this generator to be exactly the golden radio and some other results. Then other thing that we studied also related with the Frobenius-Perron dimension of the simples, and this notation is kind of generalizing or copying from group theory again. We look at the Frobenius-Perron dimension of the simples, and this will be that set, the character degrees in some sense of the category. And we put conditions. Let's say that there are only powers of a fixed prime here, or let's say that it's only 1 and 2. What can we say? And in this case, with Sonia Natale and myself, we did work to advance this. And again, a lot of the work here is more like characterize. There is a nice class of categories called group theoretical, and a lot of times knowing this let you say if the category is group theoretical or not. That means comes from groups or not. And then also Scott Morrison, Emily Peters, and Noah Snyder studied categories that are tensor generated by one object. And what they did was bound the multiplicity. So for example, you have fusion rules like these with AB simple objects, and they give also classification results in these contexts. So I want to tell you a little bit more about some results on this direction of classification. So one interesting family of fusion categories are the so-called weakly integral that I mentioned before. This means that the dimension of my category is an integer. This doesn't mean that the dimension of the simple objects are integer, but they will be at most a multiple of a square root of an integer. It will not be nothing very crazy. Yeah, and I was going to, no, I will not say this. I was going to write, yeah, exactly. So in this case, the Frobenius-Perron dimension of the objects are like this. And maybe this is Jelaki Naidu and Jelaki Nikchik for n an integer. When all the dimensions of the objects are integer, we can say much more. In that case, the category is called integral, and it's the representations of some quasi-Hopf semisimple Hopf, some semisimple quasi-Hopf algebra. But in this case, we only ask for this condition. And there is a conjecture by Ettinghoff, Nikchik, and Ostricht from 2008. So at this point, it's more than 12 years, that if your category has this condition, if the dimension is an integer, then we should be able to construct it from finite groups. In some sense, I'm not being very specific here, but this is called weakly group theoretical. What this is saying is that your category is more equivalent to an nilpotent category, and an nilpotent category can be described very nicely in terms of groups. So basically, what we are saying here is can be constructed using groups. And a lot of people have been thinking about this, and I asked also the experts, and we were kind of stuck, and we didn't know how to go, what directions to explore to prove this conjecture or disprove it. And so last year with an undergraduate student that now, or master student that now she's a PhD student, we were doing some classification of certain class of categories, and we found some ideas on how to look for a proof or a counterexample. So we focus on the case that this dimension is an integer, but it's an odd number. In this case, if you have that your category is weakly integral, so this is, maybe let me say this here, this condition here, if your category is weakly integral, then having odd rank, so finite odd number of simple objects is the same as the dimension being odd, and it's the same as your category having or the category being maximal non-self-dual. And what this means is that if X is isomorphic to the dual, then X must be the unit. The unit always has this property that it's self-dual. It's isomorphic to the dual, but maximal non-self-dual means that it's the only object that has this property. And if you are in the case of weakly integral, all these things are the same. So Brullier and Rowell proved a long time ago, maybe in 2010 or so, that if C is modular and has odd dimension and the rank is smaller or equal than 11, then C must be pointed, must be vec G omega, let's say, for some finite group. So one of these nice examples that they've talked about. A remark is that they found an example in rank 25, not of the form vec G omega. So in rank 25, still with this assumption, they found an example that it's the double of the semi-direct product of set 7 and set 3, and that it's not of this form. It's closely related to groups, but it's not of this form. So the question is, or the question was, what happened with the ranks in between, with the odd ranks between 11 and 25, or between 13 and 23, are all the categories with that ranks of this form or not? And that's what we were studying with my with Agustina Chenki, that now is a PhD student in Oregon, and we were able to push a little bit more the result of them. So what we prove is that if here the rank is up to 15, we get the same result. So let me say 15, we also get this result by this theorem, but I will not write it exactly like that. But if the rank is smaller or equal than 23, that was the ones that we were studying, or C is of this form, or the only object in C that it's invertible is the unit. So what is this saying? Here what I'm saying is that the simple objects are all invertibles. Invertible means that when you do X tensor X dual, you get the unit. I think it's also like fully dualizable or something like this. And here I'm saying that the only object with that property is the unit. The unit always has this property. Why this was an interesting finding? Some years ago, when I was doing my PhD, we proved with Sonia Natale that if the dimension of your category is odd, and here you just need fusion, and the category is weakly group theoretical, so one of these coming from groups, then the category is also solvable, which I will not say in detail what this is, but if you see it kind of a Fate-Thompson theorem, but with an extra hypothesis. Sadly, we use Fate-Thompson theorem to prove this. And one thing that I think of Nixie-Kanostrick prove is that if C is solvable, it must have one non-trivial invertible. So the conclusion of these three things here is that if you have C modular with dimension odd and the rank, smaller or equal to 23, or C is of this form, or you found an example or a counterexample of the conjecture. It cannot be weakly group theoretical. And so we have some conjectures that I will not write, but we would like to prove something like this in general for fusion categories. So we would like to have a Fate-Thompson theorem for fusion categories. If your category has odd dimension, then it must be solvable. And in that case, we could disprove this conjecture of, I think, of Nixie-Kanostrick. So I don't know if you have questions or comments for me.